It's fascinating how we often think about change, especially in huge systems like ecosystems. We expect things to happen gradually, smoothly. But when you actually look at the data, like the fossil record or even, say, earthquakes, it's not smooth at all. It's these long, quiet periods, then bam, huge, sudden events.
That's exactly right. It's one of the big puzzles in science. In evolution, we call it punctuated equilibrium.
Yeah.
You get these long stretches of, well, apparent stability or stasis. And then seemingly out of nowhere, massive shifts occur, like mass extinctions. Today, we're going to dive into a model that tries to explain exactly that. It's called the Bak-Sneppen model of coevolutionary criticality.
Right, Bak-Sneppen. And our goal here is to really unpack how this model, which seems incredibly simple on the surface, actually demonstrates something profound called self-organized criticality, or SOC, and how it connects biology to, well, physics, suggesting these big disruptive events might just be part of the system's nature.
Precisely. The model itself is starkly elegant. You imagine a set of species, say dollar of them, arranged in a circle, like a very basic food web. Each species gets a number, a fitness value, randomly assigned between 0 and 1.
Okay, simple enough. A ring of species, each with a fitness score. What happens then?
Well, here's the rule, and it's the only rule, really. At each time step, you find the species with the lowest fitness in the entire ring.
The weakest link.
The weakest link, exactly. And that species gets eliminated, or maybe you think of it as mutating drastically. It gets assigned a brand new random fitness value.
But I remember reading, it's not just that one species, is it? There's a catch.
That's the crucial part. It's not just the least fit species. That species and its immediate neighbors on the ring, the ones directly adjacent to it, are all replaced. They all get new random fitness values.
Wow. Okay, so removing the weakest link immediately destabilizes its local neighborhood, too. That feels harsh.
It is harsh, but it drives the system. This local interaction forces coevolutionary pressure. The neighbors are suddenly in a new environment because their neighbor changed.
So hold on. This suggests that mass extinctions, these big bursts, might not always need an external trigger, like an asteroid. They could just emerge from the internal dynamics.
That's the core idea of self-organized criticality, yeah. The system, through its own rules, drives itself towards a critical state. It doesn't need any fine-tuning from the outside. It naturally ends up poised right on the edge of instability. And in that state, activity happens in bursts, these avalanches.
Avalanches. So in the model, an avalanche is like a chain reaction of extinctions.
Exactly. One species changing triggers changes in its neighbors, which might then become the least fit, triggering their neighbors, and so on. A small event can cascade into a huge one.
And that sounds just like the punctuated equilibrium idea, long, calm periods, then sudden widespread change.
It mirrors it remarkably well. If you track the activity of just one species over a long time in the model, you see this pattern very clearly. It actually forms a shape called a devil's staircase.
A devil's staircase. Okay, what does that look like? Sounds dramatic.
Imagine plotting the total number of times that specific species has mutated or been replaced over time. What you see are long, flat, horizontal steps, the plateaus. That's the stasis. Nothing is happening to that species for a long time. Then, suddenly, a sharp vertical jump. That's when it gets caught up in an avalanche, a burst of activity.
So the staircase shape directly visualizes the periods of calm and the sudden bursts of evolutionary change.
Precisely. And what's really compelling is that more advanced theoretical work, looking at generalized versions of this model, confirms this. They find these characteristic mathematical patterns, these power laws, describing things like how long the stasis periods typically last. It suggests this isn't just a quirk of the simple model.
So the math holds up even when you make the model more complex.
It does. For example, the distribution of those stasis links often follows a power law like sim tau, where the exponent table can even be predicted theoretically in some cases. It points to a kind of universality.
Which brings us to the bigger picture. This SOC phenomenon, this tendency for systems to self-organize to a critical state and exhibit avalanches. It's not just in this evolution model, right?
Not at all. That's the beauty of it. You see mathematically similar dynamics in things like earthquake models, sandpiles, sliding, solar flares, even some economic models. It seems to be a fundamental way complex systems handle being constantly pushed or driven.
So for you listening, the takeaway here is pretty significant. Understanding a model like Bak-Sneppen gives you a lens to see how complexity and even catastrophe can emerge from very simple interactions. These huge, sudden events aren't necessarily anomalies. They might be the expected behavior of systems organizing themselves right to the edge. This deep dive is sponsored by embersilk.com. Silk is the answer for all your AI education and integration needs. So we've seen how the Bak-Sneppen model provides this elegant, if stark, picture of evolution driven by internal pressures, leading to punctuated equilibrium through self-organized criticality.
It really shifts the perspective, and it leaves us with a rather provocative thought, doesn't it? If the mathematics underlying biological evolution, say geological shifts, share these deep similarities,
Hmm.
what other complex systems that feel chaotic, maybe human systems like financial markets or social networks or global logistics, could they also be silently, inevitably organizing towards their own critical points, poised for sudden large-scale transformation?
That's definitely something to ponder. Thank you for joining us on this deep dive. If exploring these ideas sparked your curiosity, please do subscribe and consider leaving us a 5-star review. It genuinely helps others find the show.